So we talked about getting the continuous analog signals into a digital form, into a discrete form into the computer. We need to sample the signal in order to do that. So how do we know how fast we should sample? Well, let's return to our dear old phaser to explore this a little bit. So the phaser is moving around at a frequency. And by definition, this frequency, the direction of the vector is positive in the anticlockwise. But, of course, it could turn the other direction. In fact, it could have the same frequency, but negative and turning in the opposite direction. So, we want to look at this signal. We have a signal, we don't know so much about it, but we want to take it into the computer and study it. So, again, the vector is going to turn like this. It has a certain frequency. And we're going to sample it once every that frequency. So, imagine that we lie down here, and every now and then we open our eyes, ever so briefly, and sample what the resulting waveform looks like. So we start at time 0, and we don't open our eyes again until it completes one full circle. So we sample at exactly the same frequency. So omega sampling equals to omega 1. What will we see? Well, here we will have first a maximum, and next time we open our eyes, it doesn't look like this one has moved very much. We still have a maximum, and so on. So, in fact, to our eyes, it looks like this is a direct current. It doesn't fluctuate, nothing happens. Let's try to sample a little bit faster then. So we sample twice the frequency of the vector. That means that we get this point, but the next time we open our eyes, the vector has moved over here. Okay, so that's a negative maximum. And over here again, and over here again. So we know the extreme points here, and we can see that something happens within the fog. But actually we don't know whether the vector was moving in that direction or in that direction. In this case, it doesn't matter. This is the Nyquist frequency, the slowest possible rate that we can sample a signal at and get, and still hope to fully represent it faithfully. We might, of course, be unlucky and capture it at 0 every time, right? So if we look here and here and here, we would just get zeros. Like that. But still, the Nyquist frequency is the slowest rate which we can. What happens if we do it a bit slower? Not just once every like that, but a bit slower. Let's see. Let's maybe take 1.5, or we sample it here and here. What do we see here? So 1.5. So first up we get the point where we used to. Then we don't get the extreme down here, but we get the 0 up here. Then the next time we look, we're already over here, so down here. And the next time we look, we're at another 0 point. And if we start connecting these points, you can see that in fact that signal now looks much slower than the original signal, or the original speed, because we're looking too seldom. And in fact, we're not actually assuming here that the rotation is in that direction, but the closest connection here is in that direction. So, if we look at the frequencies, and we have 0 here, and we have the Nyquist frequency, which is half the sampling rate over here. If we have a signal, if omega 1 is in this is higher than half the sampling rate, we will observe it as a negative version like that, but at a lower frequency. And in fact, what is happening here is that it's going to be folded over. So what we see, what we observe here is the slower alias frequency of the one that is actually in the signal. This is what aliasing is. So the down point of this is that we need to at least sample twice the maximum frequency in the signal. Otherwise, we don't only lose that frequency, but we get a distorted version that appears to be at a lower frequency than what it actually is.